Okay, so what do a clap of thunder, the music you're listening to right now, and the ripples on a lake all have in common? Sounds kind of like a riddle, right? Well, the answer is this incredible hidden force that's always moving energy all around us. Today, we're going to pull back the curtain on the secret life of waves. The connection? It's all about energy in motion. Yeah, they seem completely different, but believe it or not, they all play by the exact same rules of physics. And once you get a handle on them, you'll start to see these invisible currents of energy that are literally shaping our world. Okay, so if you remember just one thing from all of this, let it be this. A wave is a disturbance that moves energy from one place to another, not stuff. I mean, really think about that. When you see a wave moving across a pond, the water itself isn't traveling across the pond. Nope, the water molecules are pretty much just bobbing up and down in the same spot. It's the energy that's taking the trip. So the big question is, how does this energy actually travel? Well, it turns out there are really just two basic ways, two fundamental moves that waves use to get from point A to B. And it all boils down to how the particles of the medium, the actual stuff the wave is moving through, get jiggled around. And these two moves have names, transverse and longitudinal. The only thing that separates them is the direction the particles are moving. Are they moving up and down, perpendicular to the wave's path? Or are they moving back and forth, parallel to it? That's it. That's the key difference. All right, first up, let's talk about transverse waves. The classic example is a rope. Just imagine you're holding one end and you flick your wrist up and down. You see that wave travel all the way down the rope, right? But think about any single piece of that rope. It's not flying across the room. It's just moving up and down vertically. That's perpendicular, a right angle, to the direction the energy is actually traveling. And now for the other type, longitudinal waves. So instead of a rope, picture a slinky or the spring you see here. If you push one end, you see a pulse of energy travel all the way to the other side. But look closely at the individual coils. They're just moving back and forth, forward and backward, parallel to the direction the wave is going. This motion creates these little bunched up areas we call compressions, and these stretched out areas called rarefactions. Okay, so we've got our two basic moves, the up and down of perpendicular motion and the back and forth of parallel motion. Simple enough, right? But now, let's see how these two simple actions create the incredible, complex waves we see and hear every single day. We're talking sound, water, even earthquakes. Let's start with sound, a perfect example of a longitudinal wave. Just look at a speaker cone. It's vibrating, right? It pushes forward and it squishes the air particles together. That's a compression. Then it pulls back, leaving a little gap of lower pressure. That's a rarefaction. It's this chain reaction of squish and stretch that travels through the air as a sound wave. In fact, it's literally how my voice is getting to your ears right now. All right, but what about water waves? I mean, they look like classic transverse waves, just moving up and down. But, and this is the really cool part, they're not. They're actually a kind of hybrid. If you could track a single particle of water, you'd see it's not just moving up and down. It's actually moving in a little circle. It's got the up and down motion of a transverse wave combined with the back and forth motion of a longitudinal one. Pretty wild, huh? Okay, to really get a grip on this stuff and, compare different kinds of waves, physicists have a specific vocabulary they use. It's like learning the language of waves. So let's break down the basic anatomy, the key parts that every wave has. Yeah, this quote really nails it. Think about it. The difference between a little splash and a giant cannonball into a pool, it's not that they make different kinds of waves. It's all about the size of those waves. And that size comes down to one thing: how much energy you blasted into the water. And in physics, that size has a name: amplitude. For a simple transverse wave, it's just how far the particles get pushed from their normal resting spot. You can think of it as how high the peak of the wave is. And here's the key: it's a direct measurement of how much energy that wave is carrying. And this shows you exactly what I mean. On the left, a little bit of energy gives you a wave with a small amplitude. On the right, you pump in a ton of energy, you get a wave with a huge amplitude. It's really that simple. It's the difference between a gentle ripple and a massive tsunami. More amplitude, more power. Always. So amplitude tells us all about a wave's power, but we also need a way to describe its shape, right? And for that, we use two more key terms. First, there's wavelength. That's just the distance from the top of one wave to the top of the very next one. And then there's frequency. which is simply how many of those waves go by a specific spot in 1 second. All right, so now we've got our basic toolkit: amplitude, wavelength, and frequency. Let's put it to the test and go back to sound. How do these purely physical properties translate into what our ears actually perceive as loudness and pitch? Well, for loudness, it's super straightforward. A sound wave with a bigger amplitude is packing more energy, and our ears interpret that extra energy as a louder sound. That's it. A whisper, that's a sound wave with a tiny amplitude. A rock concert, that's a wave with a massive amplitude. And we actually have a scale for this. You've heard of it, decibels. So quiet whisper is down around 20 decibels. Normal city traffic jumps all the way up to 85. But by the time we get to a rock concert, you're talking 105, 120 decibels. And at that point, the wave is carrying so much energy, it can literally damage your hearing. It's a huge, dramatic leap in power. Okay, so if amplitude is loudness, then what's frequency? Simple. Frequency is pitch. The more waves that pass by every second, that's a higher frequency, the higher the pitch we hear. Think of a flute. And the fewer waves per second, a lower frequency, the lower the pitch. Think of a big tuba. And this is where things get really wild. You see, we humans can only hear frequencies between about 20 and 20,000 hertz. That's it. That's our little slice of the acoustic world. But check this out. A dog can hear frequencies more than twice as high as we can. And then you have animals like dolphins and bats. They operate in a world of sound so high-pitched, it's completely silent and invisible to us. It's a really humbling reminder that what we perceive isn't the whole story. Okay, for our last big idea, let's circle all the way back to the most important concept of all: energy. We already know that a higher amplitude means more energy, but what's crucial to understand is that the relationship isn't one-to-one. It's not linear, it's exponential, and that changes everything. Here's the rule. The energy a wave carries is proportional to the square of its amplitude. Now, what does that mean? It means if you double the height of a wave, you don't just get double the energy. No way. You get 4 times the energy. You triple the height, you get 9 times the energy. A tiny change in size creates a massive change in power. And this graph just shows you that incredible relationship visually. Look at how that curve just skyrockets. A little increase in amplitude along the bottom results in a huge jump in energy on the side. This is so important. It's why a 10-foot ocean wave isn't just twice as dangerous as a 5-foot wave, it's 4 times more powerful. That squared relationship is literally the difference between a fun day surfing and a devastating tsunami. So everything we've talked about today, sound, water, even seismic waves from an earthquake, they're all what scientists call mechanical waves. They all need a medium, some kind of stuff, to travel through. But that leaves us with a giant, fascinating puzzle, doesn't it? Think about the sun. Its light and heat travel 93 million miles through the total vacuum of empty space to get to us. So how does that energy make the trip if there's nothing there to carry it? Well, that requires a totally different kind of wave. And that's a story for another time.